So today we will see how to construct confidence intervals for counted data. So counted data is counts, like when you have 1, 2, 3, 4, whatever. So you need statistical distributions to explain how the data is generated. So remind always that when we construct confidence intervals, we are going from the sample to the population, but first we need to model how things are happening in the population. So we need to assume how to simulate the data. So there are three distributions that are particularly of use in this context. One is the Poisson. So the Poisson is the distribution of the number of events that happen independently of the time that we observe. So it doesn't matter how long it is that we saw the last event, and they occur at a fixed rate, and this is important. So one of the properties of the variance is that the Poisson is that the variance of the Poisson is equal to its mean, and it is kind of constrained that we will release later. So, for instance, babies born in an obstetrics ward every day, they happen at a fixed rate, approximately, and they are independent of each other. The number of some particular kind of cells that you see in one microscope field is also, they happen independently from each other and they occur at a fixed rate. So given an area, we have a particular number of counts per area, number of units per area, and this is the same as the babies born. So the babies born is number of babies per unit time, per time unit. Also, the number of radioactive disintegrations detected by the detector in 1 minute. And so this is the Poisson. The binomial is the distribution of the number of Bernoulli successes, each one with a fixed probability occurring independently. So for instance, the number of heads that you have in 50 coin flips. So for every coin flip, the probability of observing a head is always the same. And you may note the difference here. It is we're focusing on the fixed rate in the Poisson, while in the binomial where we are looking at the probability of the success, or number of left-handed people and right-handed people in a sample, or number of male and female in a sample, and so on. So this the Poisson is rather useful, or the binomial, but there are not so many free parameters that we can tune. So the Poisson can only tune the rate. The binomial, once you have a fixed number of events, like 50 coin flips, the only parameter that you can adjust is the probability. So you have only one parameter. So the negative binomial has two parameters that you can adjust to explain the data. So the negative binomial is the count of the number of Bernoulli successes occurring independently before R failures are observed. So how many successes, each one with a probability P, you observe before observing R failures. So how many heads before observing R tails in a coin flip. And this is used because the Poisson, in the Poisson, the variance and the mean have the same value. So if you have a counted data for which the mean and the variance do not have the same value, you need some other distribution that has at least two parameters so that you can adjust them to explain the mean and the variance. And this negative binomial is very much used for that reason. And for instance, it has been used to explain the number of parasites in blood specimen, or the number of alcoholic drinks taken over a period of time incidence rate of mastitis in cattle, or whatever other count, as long as you need different means and variances. So here we have the several Poisson distributions for different fixed rates. So the fixed rate is called lambda. Lambda in this formula has been represented as NP, and the formula is NP, here it is lambda. And then what we see is, so lambda explains what is the count rate. So we see 2 counts per minute, or 4 counts per minute, or 2 counts per field, or 2 counts per period. So this per is very important. So it is how many counts per unit time, or per unit area, or per unit whatever. And for very low counts, it is for very low rates, it is a rather asymmetric distribution. But as long as the rate is large enough, it starts becoming more and more symmetric, and it looks more like a Gaussian eventually. So the assumptions of the Poisson distribution is that the event is clearly defined. For instance, if you are looking at particular cell types in a microscope field, sometimes it is difficult to determine whether a cell is really one of these types or not. So sometimes it is not so easy to define the events. And then the Poisson also assumes that the events occur randomly, independently of other events. So for instance, baby twins in an obstetric ward violate this assumption, or parasite aggregations in blood samples. So if the occurrences of the events are related to nearby events, then we are violating the Poisson distribution. Poisson also assumes that the average rate, the lambda, does not change over time, and that each event is counted only once. That was an interesting study of airplanes that were close to collide. So the researchers were asking pilots whether they were close to collide with some other plane ever, and so they were interviewing different pilots. And this, so it is a count data, so how many times you have been close to collision. And the problem was that if you ask, 2 planes were about to collide with each other, but then if just by chance you interview one of the pilots and the other one of the pilots, then you're counting the same event twice. And so the Poisson assumes that it is counted only once. Then let's construct confidence intervals. And in general, as always, the larger the sample, the better for the confidence interval, the narrower it will be. So for instance, let's say that we are interested in counting what is the number of raisins per bagel. So you take a bagel, you find 10 raisins, and assuming that the raisins do not aggregate and that the recipe does not change over time, so we are now in the regime of the Poisson distribution. So we are now constructing a confidence interval for the fixed rate, for lambda. And then with this data, the confidence interval is between 4.8 and 18.4. And note that this confidence interval does not need to be symmetric. So this is a property of asymmetric distributions, and many distributions are asymmetric. We could say the T-student and the Gaussian are among the few ones, standard ones, that are symmetric. So our observed rate was 10, but then there is a distance of 5 on the left and 8 on the right. Okay, so now if instead of 1 bagel we take 10 bagels and we observe this number of raisins, So we have a total of 100 raisins in 10 bagels. So the rate is the same. So here in the first case we had 10 raisins per bagel. Here now we have again 10 raisins per bagel. But now, since we have observed many more objects, we can construct confidence intervals that are much smaller. So we have counted 100 objects, so we construct the confidence interval around this 100, and then we divide by 10 just to get the confidence interval for the rate of bagels of raisins per bagel. So now it goes only from 8 to 12. That is much smaller than what we had before, and as we have more and more observations, the confidence interval tends to be more symmetric. You see, it is not strictly symmetric, but it is much closer to a symmetric confidence interval. So the exact confidence interval is given by this formula. So lambda is between these two values, and this is the chi-squared, and this is the alpha half percentile with 2c degrees of freedom, where c is the number of counts. So in the previous example it would be 100, not the so it is for the 10 bagels, not for the one single bagel. And this is complicated, so you can construct an approximate confidence interval, and you could do something like this. And here you recognize this property of the Poisson, where the mean and the variance are the same. So this is the mean, and this is the standard deviation, approximation to the standard deviation. So this approximation is more and more valid as the number of counts is larger and larger. So the larger the fixed rate is, the more approximate, the more accurate will be this confidence interval. So this is all for today, and see you next time.